Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's scribblecast of organic chemistry lectures and solutions to homework problems. In this scribblecast lecture, we will be examining the second substitution of aromatic rings. What happens if you attempt to carry out electrophilic aromatic substitution on a benzene ring that already has a substituent on it? If you have an aromatic ring which already possesses a substituent, these rings can be broken into two categories. If you have substituent E, I'll use the E for electrophile, let's call it F. There are those substituents on the ring that cause the molecule to react more rapidly. Than benzene. And then there are molecules which can be grouped together. I'll say they have substituent G. And the substituent causes the aromatic ring to react less rapidly. Than benzene. Now, the groups that cause molecules to react more rapidly than benzene are called activating groups. And the groups that cause the aromatic ring to react less rapidly than free benzene are called deactivating groups. Now remember that these groups are activating or deactivating towards electrophilic aromatic substitution only. This will be an important consideration in a few subsequent lectures, a few lectures from now. Now it turns out that the substituent position is also important to determining where substitution occurs. That is, if I have an aromatic ring, EFG, I can get substitution. So here's my activated ring. I have the possibility of getting substitution here. So I have a 1,2 substitution on the ring here, which would be 1,3 substitution on the ring. Or, let's fix this. Or here, which would be 1,4 substitution. It turns out that all activators are what we call ortho-para directors, because they can substitute here and here. Now, the percentage composition of the ortho and the para is not easily predicted, and so we don't attempt to do that. All we know is that all activators, all activating groups, direct substitution. Ortho and para. And that is all activators. The actual direction of the ortho-para substitution over the meta is dependent on the energy of activation of the transition state. If we compare this to our deactivators, almost all deactivators, not all, but almost all deactivators direct meta. Now, I agree that the arrows there are two meta positions and they produce the same thing. So this is acceptable. That's a meta position. And there are two ortho positions as well. So this is acceptable as a ortho position as well. So almost all deactivating groups So in the second substitution, certain substituents activate and direct ortho-para, certain substituents deactivate the ring and direct meta, and there is a rare group, which we will look at, that are deactivators that actually direct ortho-para. So there are three classes that the substituents can be divided into. Let's look at these three classes. The three classes of substituents on a benzene ring. The first are the ortho, I'm just write O, comma, P directors. The ortho-para directors. The ones we're looking at are the ring activators. And all ortho-para directors are ring activators. So that makes it easy to memorize. What kind of substituents? What kind of substituents are ortho-para directors? Well, the substituents can be identified by looking at the atom attached to the ring. The atom bonded to the ring. One has one or more pairs of unshared electrons. Two has a negative charge or 3 is singly bonded to all other, has only single bonds to it. The second class of substituent. Before I go on, note that these 3 rules are OR rules. You don't have to meet rule 1 and 2 if you have rule 3. That is, you can have one or more pairs of unshared electrons. But if you have no unpaired electrons and no negative charge but only have single bonds, then you're also an ortho-para-director. So if you meet any one of these 3 conditions, you will be an ortho-para-director and ring activator. Let's take a look at the meta-directors. How can we identify the meta-directors? Well, remember, these are the ring deactivators. Ring deactivators. The atom bonded to the ring one has either a positive charge or 2, so or 2, is multiply bonded to other atoms. So if I'm to be a meta-director, the atom bonded to the ring either has to have a positive charge or is multiply bonded to other atoms, either one of those conditions. Should be an or up there. We'll look at some examples in a moment. The third group is that rare group of ortho para directors orthopara directors that are ring deactivators. These molecules are the halogens, and we'll have to look at why they are the halogens. That is fluorine, chlorine, bromine, or iodine. Okay, let's look at some examples of each. In the first category, orthopara directors that are ring activators, we could have, and I'm going to just move this electrons. Put it under here. There's one more pairs of unshared electrons. For example, if we had an NH2 group off the ring and made aniline, aniline has a lone pair. Because it has a lone pair, it's a ring activator. Has a negative charge. Well, if we take phenol, which has lone pairs and is a ring activator, we can deprotonate the phenol and base and produce this group, Phenoxide anion, which has an O-. So the atom would have a negative charge and lone pairs. An example of a molecule that has only single bonds to it but no lone pairs would be CH3. Toluene, the methyl of toluene. The carbon only has single bonds to it. All of these are ring activators and all are orthopara directors. What about the meta-directors? Well, meta-directors can have a positive charge. In fact, we can change an NH2 group into a meta-director by treating it with acid. The NH2 will become NH3+. If we protonate the lone pair, it loses its positive charge, loses its lone pair. And you'd say, oh, it all has single bonds to it. Should be an activator, but in actual fact, the positive charge overcomes that. and NH3+, is a meta-directing ring deactivator. Multiply bonded systems, you might have something like benzoic acid, where there's a C double bond O off the carbon attached to the ring. Or you could have a benzonitrile, where we have a C triple bond N as a deactivator. Now note that all ring activators are orthopara-directors, but in deactivators there are two classes. There's meta-directors and a small subclass of ring deactivators that direct orthopara. So there you have examples. Now it is going to become important to recognize which groups are more activating and which are less activating. But we have certain issues that we need to consider about ring activators. For example, if I'm going to activate an aromatic ring to electrophilic aromatic substitution, what do I have to do? What does an electrophile seek out? What does an electrophile seek out? Electrophiles are positively charged and seek out electrons. If I want to be more attracted and come in faster to a ring, the electron density in the ring must increase. You might look at these activators and say, how does nitrogen and oxygen increase electron density when they are electronegative atoms? Well, let's take a closer look at that. Molecules that have lone pairs, like aniline, withdraw electrons by electronegativity. And you might think that that should cause the ring to have less electron density and slow down the electrophile's attack. But if I draw an edge-on view of the aromatic ring and put in its 2p orbitals, so here's a 2p, 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 and 2p. And then we draw in an sp cubed nitrogen. There's this lone pair. The NH is directed away. But even an sp cubed, which is pointed away, has a weak interaction with this pi cloud. But I, given enough energy from aromaticity, can invert. And when nitrogen inverts, it goes through a hybridized state that's sp squared. In other words, I can again draw my aromatic 2p's. And if nitrogen goes sp squared, the lone pair ends up in a 2p, which I've exaggerated its size. And those two electrons side to side overlap with the aromatic ring. That means those two electrons can delocalize into the ring. So this is shown by resonance. I'm not going to draw all the resonance structures because we're going to look at them in more detail anyways. But the lone pair can dump in its two electrons into the ring. That puts a positive charge on nitrogen and a lone pair on the ring. Now, this is a minor contributor, but there's no doubt there's increased negative charge on the ring because of this. So we can see it by interaction, side-to-side overlap of the two p orbitals, and we can see it on the ring. So nitrogen withdraws electrons by electronegativity, but it pushes in electrons by resonance, and the resonance effect is the stronger effect. That makes any group that has a lone pair, like aniline, a ring activator, because it moves electrons in by resonance. Now, this is very interesting if you compare the same thing to oxygen, which has two lone pairs. Well, oxygen can draw the very same resonance contributor. So oxygen pushes in the same amount of electron density by resonance as aniline does. But who's more electronegative? Oxygen's more electronegative than nitrogen, so oxygen withdraws more electron density. If they put in the same amount into the ring, but oxygen takes more back, who has the ring with less electron density? Oxygen pulls more back, so oxygen has less electron density. That means the ring on the nitrogen example is going to be more negative. It's going to be more activated. And so NH2 becomes a stronger activator. Such ring activation is important in understanding trends in activation strength. So let's write a summary down, if we can, of directorship, and let's write it in increasing activation. Now at the top, I'm going to start with NH2. NH2 is going to be our most powerful activator in our list. It's only going to be one molecule we're going to put above it, and we'll look at that later. Okay? This includes NHCOR, substituted amines, and CH3 twice. Below NH2 will be OH. OH is a lower activator than the N because oxygen sucks a little more electrons back by electronegativity. OR is just below OH. Then we have a nitrogen group. Which has a lone pair, but a C double bond O, R. Now, why would this type of group, which has nitrogen, which isn't as electronegative of oxygen, be below oxygen in activation? I thought oxygen dumps in the same amount of electrons, but by resonance, but withdraws more than nitrogen, so the ring has less electrons. If we look at the ring, in this case, let's use a CH3 for R. I can draw resonance structures dumping this lone pair into the ring. But what's interesting is I can draw a minor contributor where I move the lone pair away from the ring. Now, if I do that, I get this. You say, wait a second, that's an N positive attached to the ring. That should be a meta-directed deactivator. Remember your rules about resonance structures. Neither of these structures exists. What exists is a resonance hybrid, which is some superimposition of this and all the structures. So there's going to be resonance structures where I move the delta minus around the ring as well. For example, I'll draw one more resonance structure here. I might do this, where the lone pair moves towards the ring. Boy, having trouble drawing my rings. Oh well, we'll go with that anyways. So, I've got my H. Now if I look at these structures, what is obvious? What is obvious is this resonance structure suggests some of that lone pair is delocalized away from the ring. That is, not as much as dumped into the ring because part of it is moved out and away. Part is moved in this direction. So resonance isn't pushing as much electron density into the ring. Also, the positive nitrogen contributor helps increase slightly the electronegativity of that nitrogen. So overall, less electron density gets put into the ring. Just enough, not a huge amount, just enough to knock that nitrogen below oxygen in strength of activation. Next will come C6H5, which is our benzene. Why would a benzene attached to a benzene be an ortho para director? Well, no matter how you draw the resonance structures, when you have something like this, you can do that. And yes, one ring will lose electron density, but whenever one ring becomes electropositive, the other ring becomes electron rich and is susceptible to more greater attack, if you like. So we would get something like this. Minor contributor, and while this ring would not be susceptible to attack, this one certainly would. So because you can draw resonance structures, because the two P's coming off these rings overlap side to side here, there's delocalization of electrons, and more rings means more electron density. But again, because you put a positive over here on this ring, it's not greater than what you get with oxygen and nitrogen. Below that are the alkyl groups, methyl, ethyl, etc., where R is alkyl. These molecules are deactivating. The weakest, sorry. These molecules are activating, but the weakest activating because they can't do resonance. If you have a methyl on a benzene ring, the only way you can push electrons into the ring is by inductive electron donation. Inductive electron donation through the sigma bond from carbon leads to a slight increase in electron density. this slight increase is not as great as what occurs in resonance. Now, the last group that I'm going to list here are the halogens. I put them here even though they are deactivating. This is where the demarcation is. They may be deactivating, but if you like, they're the weakest deactivators. So right in here is benzene. Everything above this line reacts faster than benzene. Everything below this line reacts slower than benzene. And we're going to have to take a close look at halogens to explain why it's both deactivating and ortho para-directing. All the other groups are ortho para-directors. Now at the top of this list, I can make oxygen less electronegative and make it a stronger activator than aniline by taking these neutral substituents, deprotonating them. If I take oxygen and make it O negative, pull the proton off. O negative is more activating than NH2 because the electron, the negative charge, satisfies some of the electronegativity of the oxygen, allowing the resonance effects of dumping in electrons. If you like, the negative charge helps donate more electron density into the ring than neutral aniline can. And likewise, if you deprotonate the NH2 and make it NH minus, it goes even higher. So there are other activators we can put in this list. What about the meta-directing deactivators? So, what can we say about them? Well, I can give you a list of deactivators. Okay, and this is increasing activation. I'll draw in an arrow. The most activating is at the top, so that's increasing activation. Now we have meta directors. All these molecules, or these fragments of molecules, substituents, attached to an aromatic ring, are meta directors, and they are deactivating. Notice as we increase the number of electronegative atoms off of the carbon attached, or the atom attached to the ring, as it becomes more and more electronegative, we're withdrawing more and more electrons. We become more and more deactivating. Or sometimes increasing the multiplicity of the bond can help. But as electronegativity increases, deactivation increases. So if we were to write this, we have CO2R, SO3H, CHO is an aldehyde, CO2H, CN, NO2, and the most deactivating in this list, the most deactivating is NR3+, where R can be an alkyl group or hydrogens. In this case, the strongest deactivators are at the bottom. So this is increasing deactivation. And this list would fall right below the halogens. So there is a list you need to memorize of your orthopara directors that are activating, your halogens, which are orthopara directing but deactivating, and your meta-directing deactivating groups in increasing deactivation and increasing activation. All right. What we need to do now is begin examining each group and try to rationalize why. Why do we get direction in the way that we do? Now, we're going to begin by taking a look at the reactivity of aniline. And there are two things we have to explain. One is reactivity and one is orientation of attack. These are all explained by looking at the resonance structures of the rhenium ion, which is related to the benzenonium ion. And you may notice me occasionally referring to the rhenium ion as a benzenonium ion. In actual fact, it is a substituted benzenonium ion, but please take note of that. Let's start with aniline. I can explain, just better change my color back. I can explain the reactivity in aniline by the following resonance structures. NH2 has lone pair. And I can dump those electrons in and move the pi electrons out here. And I can draw this resonance contributor. I can continue to move the lone pair around the ring. Continue to draw resonance structures by moving the lone pair around the ring. Notice when I dump the lone pair, I must move the pi bond away or I create too many electrons around the carbon. We're simply following the resonance structures rules you learned in the opening lectures. Till at last we've gone full circle. This is dumped in. Those pi electrons move back out. and then H2 has its lone pair back. How does this explain the reactivity? Reactivity, remember, indicates that aniline is an activator. We can explain its activation by looking at the negative charges. Resonance actually places negative charges around the ring. This increased negative charge on the ring attracts electrophiles faster. It causes this substituted benzene to react faster than free benzene. It is an activator, an activated ring, because of increased negative charge by resonance. We could draw the exact same structures if we put OH with two lone pairs. So this type of resonance explains not just NH2, but it also explains phenols. We can explain the ranking as we did. If we could draw the exact same structures for phenol, the negative charges we put in these positions on the ring must be slightly more reduced in the phenol case because oxygen's more electronegative. So oxygen's a little less activating. You'll notice that this reactivity set of structures can also explain ortho-para direction. What do I mean? Take a look where the negative charges are. The negative charges have appeared here, here, and here. Where are those positions relative to the nitrogen? They are ortho-para. Electrophiles are going to attack where the greatest negative charge appears. So this type of resonance structure also can explain ortho-para direction. Now we're fortunate that it does so. Often that's not the case. There will be examples where there are no resonance structures to explain ortho-para direction. And in that case, you'll have to consider individual sites of attack in order to explain the ortho-para orientation. So we're going to do that for every case. And if asked on a test, just to indicate why it's an ortho-para director, this is all you have to draw and explain that the negative charge is in the ortho-para positions. That's where the greatest negative charge is. That's where the electrophile attacks. But if the question states, explain ortho-para direction by considering each site of attack individually, then you will have to consider all three possible attacks and use the resonance structures you generate for each possible attack to explain. What do I mean? Well, in order to explain orientation, that is why we get ortho-para substitution, in order to explain orientation, you must consider each site of attack individually. So we're going to consider ortho attack first. Ortho attack first. We're going to take our aniline. We've got our NH2 here. Put in a pi bonds. And we're going to add an electrophile. E plus comes in and attacks. Now we add the electrophile. Here. We'll put it on ortho. When these pi electrons go to electrophile, that puts a positive here. And we begin to draw resonance structures. If you like, we're drawing where a positive charge moves in the substituted benzene-onium ion. You'll have to be able to draw these on a test. I'm slowed down by the pen I'm using to write on this computer and try and keep it legible. Now this positive ends up next to a nitrogen who has a lone pair. The lone pair can dump in, and I can get this structure. Now I want you to take note of this resonance structure because it's going to be very important to our discussions later on. Next we have pair attack. Let's look at pair attack next because if it's favored, if ortho's favored, so is para. So let's look at those two together. If we get para substitution, the electrophile goes on the para position. So we will get something that looks like this. We've got EH. We get the positive charge on the ring. We have our NH2. So, like when these pi electrons move out and the E attaches para, we're going to get a positive charge in this position because the pi electrons move away from that carbon. I can now move these pi electrons here which will give me the plus again next door to my NH2, which has a lone pair. Now, I can continue. Moving the positive around the ring. Or I could have dumped in the lone pair. From this guy. If I did, I'd get this guy. Where the plus ends up on nitrogen again. Oops. Now let's consider meta-attack. Notice when you answer a question where you consider each site of attack individually, you must draw structures for each attack. Ortho attack, para attack, meta attack. You must consider each one individually. And you draw your starting material, whether it is phenol, aniline, or even a chlorobenzene. You draw it the same way in all three attacks. And the electrophile you use is just E+. Some random electrophile. Now, let's do meta attack. Let's consider meta attack. Meta would be this position. I'd still have my pi bond here, my pi bond here, but this would become positive. I can move that pi electron there. And I get the plus here. And then I can move this plus here. Notice I'm moving the pi electrons towards the positive charge. They're attracted to the positive charge, which causes the positive to shift position, because when you move the pi electrons, you're taking electrons away from a carbon. So there you have three resonance structures, and you'll notice that the positive charge never ends up next door to the NH2. You cannot dump in the lone pair. Only ortho and para attack produce the fourth resonance contributor, which is circled in red. This extra contributor means the positive charge is further delocalized. That means in the ortho para attack, the substituted benzenonium ion is more resonance stabilized than in meta attack. That means it's a lower energy intermediate. Likewise, the corresponding transition states for ortho para attack will be lower energy because they're similar in structure to the benzenonium ions. If the energy of activation, because the transition states are low energy, if the energy of activation is low energy in ortho para attack, then meta attack, ortho and para attack will predominate. An activator lowers the energy of activation for substitution, in this case ortho and para, and it's done by producing more resonance contributors in the substituted benzenonium ion. 4 contributors instead of 3. It's that simple. This leads to ortho para attack. The stabilization, lowering of energy of activation caused by greater delocalization of the positive charge. Now this applies to this is the type of structure we would have for every ortho para directing group. Now this took so long to draw, I'm going to change the NH2 in each case to a different group. And you'll see you get the exact same structures. It doesn't matter if this was an NH2 or, for example, an OH. If this was an OH, I'd just put OH right across the board. OH. OH has 2 lone pairs. The pen is acting up. To have a lone pair here. There's OH. Works for phenol. I could draw all of these same examples where there was an OH in place of the NH2. Why are the halides ortho para directors? Chloro, bromo, iodo, fluoro, they have 3 lone pairs around the X. I'll use X here. Change the OH to X. X marks the spot. And X has 3 lone pairs. So when you've dumped it in and you make X positive, there are 2 lone pairs left. Look at that. You can draw the exact same structures for the halides. This type of set of resonance structures explains the orientation of attack, why we have ortho para directors for oxygen, nitrogen substitution, and even the halogens. Even O- can be explained this way. Replace the X with an O-. 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 No matter what you've got, you can draw the exact same resonance structures, in which case this would be O neutral then, because the negative charge gets neutralized by the positive charge. So you can put any groups whatsoever in these positions. Apologize for the noise. Obviously, there's some construction going on upstairs. I have no idea what's going on. Okay, what about when we put a methyl group on the ring? And we're going to consider orientation of attack. Well, now we lose two resonance structures. If there's a methyl here, and I do my substitution, I cannot draw the fourth resonance contributor. There's no pi bonds, lone pairs of electrons on methyl to dump in when the positive charge is next door to methyl. I lose this structure. I lose the structure labeled red. If I do this for all the others, I also lose it in the case of para attack. If I have CH3s, these change to CH3s, para attack, I get these structures. Now, at first glance, if I change to CH3, there seems to be no difference in the resonance stabilized substituted benzenonium ions for ortho, para, or meta attack. But what's interesting and what's different is if you look closely. Again, an ortho para, the positive charge ends up next door to the methyls in these structures. Here for ortho, and here for para. Because the positive charge is next door, the methyl is capable of inductive electron donation right into the positive charge. Putting a positive charge beside a group that inductively donates electrons is especially stabilizing. It makes these two resonance contributors more major contributors and greater contributors. That's redundant. More major contributors and greater contributors. It makes these resonance contributors more stable. Hence, the ortho attack and para attack resonance stabilized substituted benzenonium ions are more stable than that of meta attack because the positive charge never ends up next door to the inductive electron donating methyl group in the meta attack case. So once again, ortho attack and para attack is favored. It's not as stabilizing as resonance and further delocalization, but there's still a stabilization factor. Now, what about the halogen case? If the halogen actually directs orthopara and dumps in electrons by resonance, why is it a deactivated ring? As we saw, if the halogen dumps in electrons to the ring by resonance, so I can draw the same structures that explain reactivity. Site of reactivity being ortho para for halogens. Now I can move the electrons around. So there's a positive on X. Negative charges appear at the ortho para positions in these structures. Negative charges appear in the ortho para positions, and therefore the electrophile goes for the ortho para attack. But these resonance structures show that the negative charge is increased on the ring. The ring should be activated. Why are halogens deactivating? Halogens prefer to be monovalent. In this rare case, electronegativity wins out with regards to ring activation. The side-to-side overlap of the 2p, 3p, 4p, 5p orbitals of fluorine, chlorine, bromine, and iodine is less efficient due to electronegativity. Remember, fluorine's the most electronegative of atoms. And if electronegativity wins out, more electron density is removed than donated by resonance. And so for reactivity, while we can use this resonance structure, to explain ortho para attack, we do not use it for the halogens to explain activity, but rather we draw this. Draw the halogen, put an arrow and a delta plus on a ring. Electronegativity is used to explain the reactivity of the ring. So the halogen exception we attribute to electronegativity effects, but we do use resonance to explain the ortho para attack. Well, for the second substitution, that just leaves all that is left now are the ring deactivators. How can we explain the reactivity of the ring deactivators? Well, we can start, and let's use one of the most deactivating groups, nitro. We can start by drawing a nitrobenzene. Now the first resonance structure I'm going to draw, let's get a little more room. Running out of room. Will not reveal much with regards to reactivity because it's just going to interchange the ring pi electrons and the NO2 pi electrons. And certainly this is a legitimate resonance contributor. And I'm only drawing it to show that yes, we can draw other resonance contributors that don't really tell us much about the reactivity. So certainly these two guys are resonance contributors of each other. But what's interesting about nitrobenzene are the minor contributors we can draw, where we move pi electrons towards the nitrogen, the positive charge. Pi electrons move towards the positive charge. If I do that, I get minus, minus. There'll be double bond here. They'll have a plus on the nitrogen and a plus here. These pi electrons can move towards that plus. Lots of charges to draw on this one. Move those pi electrons here. Putting on the N again. We got negative. Oxygens have negative charges and a positive. And so we now can move back to one of these two structures. We can actually go back to this one. Okay, so there you have the resonance contributors that allow us to understand the reactivity. And look what's happening to the ring. First off, the ring is deactivated because we're moving electrons out of the ring. The ring moves positive charges around the ring. Electrophiles come in less quickly because the ring bears an increased positive charge. Less negative charge attracts electrophiles more slowly. Secondly, look where the positive charges end up. The positive charges actually end up in the ortho para positions. Well, if you're an electrophile, you go for where the greatest electron density is, and that's not where the positive charges are. Hence, electrophiles will prefer to attack the meta position. Of course, as in the previous case, you could be asked to explain why this is a meta director by considering each site of attack individually. If you are required to look at each site of attack individually, you must draw out the resonance stabilized substituted benzenonium ions. For ortho, para, and meta attack. So let's start with ortho. Suppose I have a nitrobenzene. And I hit it with an electrophile. And the electrophile, in this case, adds ortho. So I'm going to do ortho attack first. So ortho attack. I get an E, an H. I have my NO2. And I get a positive charge here because the pi electrons have moved out to bond to E. Well, these pi electrons can move towards the positive charge. I get my NO2. I still have the E and the H here. And I get a positive charge here. I now move pi electrons towards the positive charge. If I do that, oops, let's draw the electrons in the right place. Still have E and H. Oh, it helps if you draw the ring correctly. There we go. Don't change the orientation of your ring. There we go. You have E, H. We have a positive. And notice nitrogen, if you check the NO2 structure, is positive. That is, an NO2 group has an O minus and a double bond O. The formal charge of nitrogen is positive. Now, let's consider para attack. Well, if I do the same thing, E plus, and I get para attack, I get E, H, Grabbing the pi electrons here, I will get a plus here. H. Plus, plus. And then finally, plus here, and NO2. And lastly, let's take a look at meta attack. In the case of meta attack, attack by an electrophile E+. Let's put the pi bonds the same way. If E attacks meta, we'll get this benzenonium ion or substituted benzenonium ion. These pi electrons can move here. I'll put the plus here. The pi bond here and here. This pi bond can move, giving me this resonance contributor. Plus there. Now we've drawn all the resonance contributors, all of the resonance contributors for the ortho, para, and meta attack. We've considered each site of attack individually. The resonance stabilized substituted benzenonium ions, in this case, there's 3 each. There's no increase in number. Initially, they look all the same. But if I look closely at this resonance contributor for ortho attack and this one for para attack, I see 2 adjacent positive charges. If I remember my rules for resonance, which were covered several months ago, adjacent positive charges are repulsive and unfavorable, making these 2 contributors minor. In the case of meta, the positive charge never ends up next to a nitrogen, so you don't get the adjacent positive charges. That means the ortho-para resonance structures have a less favorable resonance contributor. They become higher energy, and the corresponding transition states are higher energy, which gives ortho-para attack a higher energy of activation. It's less likely to happen. And meta attack is favored. So ortho-para does not occur. Meta is major. And in this case, we've explained it by considering each site of attack, the orientation, each site of attack individually. Okay, so we have looked at our three groups. We have examined the ortho-para activating directors and used resonance to explain it. We have used resonance to explain the ortho-para direction of attack for the halogens, but discovered we had to use electronegativity to explain reactivity. And we have used resonance to explain why the deactivators, such as nitro, are meta-directors. And we could do that both by drawing one set of resonance structures, which show the reactivity, or three sets of resonance structures by considering each site of attack individually. Well, that's it for the second substitution. I'm Dr. Brian Lloyd. This is my Scribblecast,